one of the big ideas in chapter 4 is being able to look at different types of equations and try to come up with the best strategy as far as trying to solve them. A lot of times we look for algebraic ways of doing it, but you also have to think sometimes about, okay, could I graph this? Maybe there are alternative ways that we can attack it. But on problem number 15, you were faced with this equation where we did the square root of 2x plus 3, and that was equal to x. And most likely the strategy most of you took here would be to get rid of that square root. So if I decided to do that, I can get rid of that square root because it's already isolated by squaring both sides. So let's see what we would have once we did that. Well, that would just leave us with the 2x plus 3 part. And then we have x squared on the other side. So this is one of those equations with x squareds and x's, so we know we want to get it equal to 0. So I'm going to do that by pulling everything over here with the x squared. So I'm going to have minus 2x minus 3. And so now I have it equal to 0. Then I look to see, okay, can I factor it? And this one we can. So I can multiply to get negative 3 and add to get negative 2. And so I get two solutions here. I get the fact that x is equal to 3, and I get the fact that x is equal to negative 1. So I look at those two solutions, and it's always a good idea to check and see, all right, I did all this work, did I do it correctly? So what I'm going to do is I'm going to plug those values in. I'm going to see how well I did. So let's say I plugged that 3 in. Well, now I've got the square root of 2 times 3, or 6, plus 3, and I want that to equal 3. And I check it out. 6 plus 3 is 9. I know the square root of the square root of 9 is equal to 3. So it looks like x equals 3 works. Then I'm going to plug negative 2 or negative 1 in. So now I'm going to have 2 times negative 1 or negative 2 plus 3. And I'm now looking at the square root of 1 and checking to see if it's equal to negative 1. Well, we know when we take the square root of 1, unless they designate that we're going to look at both the plus and the minus part, it's not going to equal negative 1. So even though I did all the steps, even though I did the algebraic part right, I actually ended up with a solution that did not work. Well, that problem has what's referred to it as an extraneous solution. What an extraneous solution is kind of like what the name says. It's an extra solution. It's one that, yeah, we did all the work, we did the algebraic steps right, but we actually came up with a value that did not fit into our equation. It was actually not a solution. Now, you may be asking, all right, well, how in the world can I figure that out? How do I know when I have that extraneous solution? Well, one thing you might look at is, well, what would the graph of this situation be? And how could I use the graph to help me find a solution? Well, one way I can think about this in terms of a graph is if it really is an equation, that means the left side of the square root of 2x plus 3 should have the same value as the right side. And that's when the value is x. So what I'm going to do is I'm actually going to create two equations. One where y is equal to the left side, the square root of 2x plus 3. And I'm going to set up a second equation where y is equal to the right side, or in other words, y equals x. Because if I gave you that system of equations where I said y equals that square root, and then I said y equals x, probably the first thing you do is set them equal to one another. So if I were to type those two things into my calculator, and I know you can't see my calculator right now, but you'll see the graph here in a second. I'm going to do the square root of 2x plus 3, and then I'm going to create a second equation where y equals x. And so here's the graph that I end up with. Well, you'll notice when I graph those two equations, I really only have one intersection. And that one intersection would be the solution that we came up with, which in this case was when x was equal to 3. So the graph actually showed me that there's only one solution that I would end up with for this equation. So sometimes when we're faced with an equation, we might ask ourselves, all right, well, how many solutions should I be getting here if I were to think about the graph? Sometimes, though, again, we end up with that extraneous solution. So you have to be a little bit careful. All right, number 18 gave you this equation. It said, okay, we're going to solve, and they gave you a full kind of story behind all this, but we're going to solve this equation. 2x squared plus 5x minus 3 is equal to x squared plus 4x plus 3. All right, now let's think about what our graphs would be if we were to split this one up. Well, the left-hand side, that 2x squared plus 5x minus 3, well, that would be a parabola. The right-hand side, the x squared plus 4x plus 3, well, that would also be a parabola. So I'd have to kind of picture, if I have two parabolas, how many intersections could I have? Well, if I look at two parabolas, I can have a variety of different numbers of intersections. So let's see how many solutions we end up with this one, and we'll see if that matched what I could have as far as intersections are concerned. So if I were to try to attack this one, we probably, again, want to get it equal to 0. So I'm going to subtract x squared. I'm going to subtract 4x, and I'm going to subtract 3. And once I do that, I'm going to look and see if we can factor it. And for this one, we can. And I figure out I've got x is equal to -3. I've got x is equal to 2. Well, again, it might be a good idea to see if I really should have that many solutions. One way you can check that is we could plug it in and see if both of those solutions work. Another way we can do it is we could check the graphs and see if they actually intersect each other in two places. So calculator's going wonky again. All right, so here's my graph. And we said over here at -3, looks like it intersects there. At +2, we can barely see it, but it looks like it intersects there. So it looks like I'm not going to have any extraneous solutions. And again, I can plug those values in to figure out if they worked or not. So really what we found here were two solutions. And those two solutions were where this side of the equation, that graph, intersected this side of the equation, that graph. Well, then in that problem, it talked also about, all right, well, somebody else came up with this equation, y equals x squared plus 6, or plus x minus 6. And they tried to solve it. We usually, when we tried to solve this, we looked at it when y was equal to 0. Well, that matched the equation we just dealt with. So we do the exact same steps as far as factoring, and we get the exact same answers. But this is really a different situation in terms of the graph itself, because what I really found here was, when is this equation, x squared plus x minus 6, equal to this, y equals 0? Or in other words, what we just found was the x-intercepts for a single parabola. So even though we got the same two solutions, even though we got the same equation at one point in our strategy, we were kind of looking at two different situations, because the first one was really thinking about two different parabolas and where do they intersect, versus the second one was thinking about one parabola and where's it intersecting the x-axis. And I know sometimes that seems a little bit confusing, but we really have to think about, all right, what are we talking about in these situations? Are we talking about a single graph? Or are we talking about maybe multiple graphs? All right, well, on number 19, you were faced with this situation where we had 20x plus 1, and that was equal to 3 to the x power. Well, you might have had some trouble with this one as far as algebraic steps. A lot of times what I hear people say is, okay, well, I want to get x out of the exponent, so I'll do the x root, which seems to make sense because that would maybe get us down to 3. The problem is, what in the world is the x root of 20x plus 1? If I don't know what x is, it's hard to deal with that one. So maybe that's not the best strategy. So I kind of get stuck as far as algebraic steps are concerned. But now we know we could also think about, well, the left-hand side, if I made it an equation, should be equal to the right-hand side if I were to make that an equation. Or in other words, if I looked at the graphs of those two, I'm really going to try to figure out, well, what's the intersection of those two? So if I look at the graphs of those two, I first of all would want to find out, well, how many times do they intersect each other? And then secondly, I'd want to see, all right, where are those intersections taking place? Now, when you looked at the graph of this one, it was pretty steep when you looked at the 20x plus 1. I'm sorry, my calculator's kind of going off a little bit again. So when I first graph mine, it looks like this. Well, it's hard to see. In fact, it's impossible to see any intersections on this one. So I've got to play around with my window. So if you're using your graphing calculator, we've got to find some values that are a little bit larger there in the x portion, or sorry, in the y portion. So I'm going to kind of play around with it, see if I can find out my intersections. So let's see, I'm going to go all right, so I kind of played around with mine and I find out that there are two intersections. So remember, to find those intersections on the calculator, excuse me, on the calculator, we're going to hit the second button, the trace button, because what we're going to look for is the calculation, and we're going to look at the intersect. So if I do second trace to get to the calculate, I'm going to do the intersect, and I find out my first intersection, cover this up, is at 0, 1. Then I'll have to go through those same steps, the second trace, intersect. Now I've got to move it over closer to where the second intersection is. what's going on. There we go. All right, so my second intersection is at 481. So I have two intersections, which means I have two different answers. This is actually just intersection. But think back to the equation. Well, the equation only had x in it. So really, all I'm concerned with is the x value. So for this one, x would equal 0. That's one solution. And over here, x is equal to 4. That's our second solution. So sometimes we'll be faced with equations where we've got options. We can do it algebraically, we can do it with a graph. Sometimes we may be limited. And in this case, our only option was to do the graph because there was no algebraic way of attacking this one. So again, one of the main ideas of this chapter is, okay, how are we going to attack these equations and what's the best way to find the solutions? Well, then we need to carry that over to situations that we have systems of equations. So in part C on number 36, this is a problem that we have the equation y squared is equal to x, and we have a second equation y is equal to x minus 2. Now, in this system of equations, we have an x and a y. So that means eventually I need to have a solution for the x and the y. Well, before I even start in on things, what I usually like to ask myself is, well, how many solutions could I get here? So if you look at that first equation, x equals y squared is a sleeping parabola. The second one, y equals x minus 2, well, that is a line. So if I think about it, if I have a line and I have a sleeping parabola on the same set of axes, I'm looking at a situation where I could have up to 2 answers. It doesn't mean I have to have 2 answers, but that would be the maximum that I could have. So I'm going to keep that in the back of my mind as I try to solve this one. Well, let's think about a way we might be able to solve this one. You can do a couple different things. Some of you may have looked at it and said, okay, x equals y squared. So that means I'm going to take the y squared, I'm going to plug it in for x. So that would be a good strategy. Some of you might have said, okay, well, if y equals x minus 2, then I'm going to take x minus 2, that entire thing, and I'm going to plug it in for y. Or in other words, we'd have now x minus 2 squared that's equal to x, and you might have solved it from there. If I were attacking this one, it doesn't mean it's the only way, but if I were attacking it, I would probably say, okay, x equals y squared, so I'm going to plug that in right here. So here's the equation I have now. Y equals y squared minus 2. And this is one of those situations where we want to get it equal to 0 since we have the y squareds and y. So I'm going to subtract y to get it equal to 0. Now we can start factoring if possible, and in this one we can, because I can multiply to get negative 2, add to get negative 1. And so I get 2 y values here. I get a y value at 2, and I get a y value at negative 1. But we know that the original equation also had an x in it. So I'm not done yet. I still need to figure out what x is. So I've got 2 situations. I'm going to start with when y was equal to 2. Well, I can go to either equation. I'm probably going to go to the top one there. Well, the top one says take the y and square it, and that'll be x. So x is equal to 4 for that one. Same deal with negative 1. I'm going to plug in negative 1 and square it, and that'll be x. So x is equal to positive 1. So here's what's going on. If I were to graph that sleepy parabola, and then I were to graph that line, I'm going to have two intersection points. One of them will be at the point 4, 2. The other one would be at the point 1, negative 1. And those would be our solutions. So if the equation only has an x in it, like the previous problem, then I'm only going to have answers that say x equals such and such. If the equations have x and y in it, then my answer should have an x and a y in it. And in some cases, we may have multiple points, not just one point. A lot of the equations we've done in the past has been like 2 lines, so we've only had 1 point. But now we can get multiple answers. All right, then you got to 37. So first of all, let's think about what's happening in 37. Well, in 37, we got x squared plus y squared is equal to 25. Well, hopefully you recognize that's the graph of, or an equation of a circle. Then we have y equals x squared minus 13. Well, we know that's going to be a graph that is a parabola. If we think about all the possible intersections I can have here, I could have up to 4 answers because that parabola could cross that circle up to 4 different places. Now, it doesn't mean we have 4, but that would be the maximum we could ever get. All right, how are we going to solve it? Well, if we start looking at this algebraically, probably the first thing a lot of you did was it says y equals x squared minus 13. So you probably said, okay, well, I'm going to plug that in for y in the first equation. So let's say I took that strategy. So I said, okay, I've got x squared. Now I'm going to plug in x squared minus 13 for y, but I've got to square that, and that's going to equal 25. And then I started going from there. So I've got x squared. If I squared this one, that would mean I'd have x to the 4th. I'd have negative 26x squared plus 169 is equal to 25. Well, now I'm staring at an equation that has an x to the 4th in it. And it's not that that's impossible to deal with, but we honestly haven't done very many, if any, where it's been x to the 4th in there. So you might have got stuck at that point. So let's go back and see if maybe I could get to a different equation that would be a little bit easier to work with. Well, if we look at the 2 equations there, you might have noticed also that, well, this equation has an x squared in it, and this equation has an x squared in it. Well, because they both have an x squared in it, maybe a strategy I could use is thinking about, all right, let me get x squared by itself in that second equation. Well, I could get x squared by itself by adding 13 to the other side. Here's how that helps me. Now I can take that y plus 13 and I can plug it into the first equation where the x squared used to be. And now I have an equation that I'm probably a little more familiar with. So I'm going to rearrange this one where I can get it equal to 0. So over here on the left side, I had the y squared and I had the y. If I subtract 25, I now have negative 12. And this is a heck of a lot easier to deal with than what we had before. So if I try to factor this one, I can do y plus 4 and y minus 3. Which means I have 2 y solutions, y equals 4 and y equals 3. Now let's figure out what x is. Well, remember x squared was equal to y plus 13. So I'm going to plug negative 4 in. So now x squared is equal to negative 4 plus 13. Or x squared is equal to 9. Here's where you have to be careful. When I square root that, remember I've got 2 possibilities. I've got positive 4, I've got negative 3. So right now I have 3, -4 as an intersection, and -3, -4 as an intersection. Then I move on to the other y value. Well, our other y value was +3. So x squared is equal to +3 plus 13. Or x squared is equal to 16. Again, when I take the square root, I'm going to have two possibilities. So I'm going to have +4, +3, or -4, -3. So just like we mentioned, it was possible to have 4 solutions. And in this one, we actually did have 4 solutions on that. All right, now you may have asked, well, was it possible to do this other equation that we had, the one that had the x to the 4th? Let's see if we could have attacked that one still, even though we hadn't dealt with that very often. Well, I've got the x to the 4th. If I put x squared minus 26x squared together, that's minus 25x squared. If I subtract the 25, I have 144. So here would have been your goal on this one. You would have been trying to multiply to get 144 and trying to add to get -25. And that would have helped us with our x values. Well, I could actually do this because x to the 4th is x squared and x squared. I can get 144 by using -9 and -16. And -9 plus -16 is -25. So I would have had two situations. I would have had x squared minus 9 equals 0. I would have had x squared minus 16 equals 0. And so I could have gotten to the same place because I get the x squared is equal to 9, which again was plus or minus 3. I got x squared equals 16, which would have been plus or minus 4. And then we would have had to plug them back in. But probably a better strategy here, just because it gave us a better equation or an easier equation to work with, was just recognizing the x squareds in both of those two equations. All right, so a lot of different types of equations that you did there. It's really about strategy right now. It's really about, okay, what am I going to be comfortable with? What's actually something that I would be able to do? And then trying to apply that. And that's going to be, again, one of the main concepts that we work on in this chapter.